Swayam Prabha. Digital India. Educated India.
Welcome back for the problems on material balances for systems which have multiple reactions. In the earlier lectures, we saw examples where reactions were happening in parallel, and we tried 3 different techniques for solving these material balance problems, namely the molecular species balance, atomic species balance, and the extent of reaction methods. I had asked you to try the last problem using molecular species balances to see whether you fully understood the technique which we have discussed. I hope you have done the exercise. Now let us move on to an example problem where reactions are happening in series. Let us look at this example problem. Formaldehyde is produced industrially by catalytic oxidation of methanol according to the following reaction. Methanol reacts with oxygen to form formaldehyde and water. Unfortunately, under the conditions used to produce formaldehyde at a profitable rate, a significant portion of formaldehyde reacts with oxygen to produce carbon monoxide and water in the given reaction. Assume that methanol and twice the stoichiometric amount of air needed for complete conversion of methanol to the desired product are fed to the reactor. Also assume that 90% conversion of methanol results and that a 75% yield of formaldehyde occurs based on the theoretical production of formaldehyde by reaction 1. You are asked to determine the composition of the product gas leaving the reactor. As the product gas stream is leaving in the gas phase, we will assume the basis in terms of moles, thereby we can get the final values also in moles and perform calculations in a simpler way. For this reason, we will assume the basis to be 100 moles of methanol fed. Based on the basis and the information given to the problem, we have 100 moles of methanol entering the reactor along with air which would contain 21% oxygen and 79% nitrogen, which reacts in the reactor to form different components. So you have the unreacted methanol leaving, and you also have formaldehyde leaving, carbon monoxide, water, oxygen and nitrogen which are leaving the system. Now that we have the flow chart to describe the process, let us try to solve this problem. As we have used the basis in terms of moles, we cannot start with total balance equations because total moles of a system is not conserved during a reaction. So instead we will start with the component balances. The first component for which we can write a balance equation would be methanol. So let us start with methanol balance, CH3OH. So the equation would be input minus output plus generation minus consumption equals accumulation. So where which of these terms will go to 0? At steady state, accumulation goes to 0. Methanol is a reactant and it is not being generated, so generation term goes to 0. So we are left with input, output and consumption. So the output term which we need to calculate would be input minus consumption. Based on the basis we used, we know that the input of methanol is 100 moles. We need to now know the consumption of methanol. We have been told that the consumption of methanol, the conversion of methanol is 90%. So using that, the consumption can be calculated as 0.9, which is the conversion times 100, giving you the total consumption as 90 moles. So therefore the methanol which is leaving the system would be O, which equals to output is NCH3OH moles, which is 100 minus 90, giving you 10 moles. So 10 moles of methanol is leaving the system. The second component we can write a balance equation for is formaldehyde. So again we start with input minus output plus generation minus consumption equals accumulation. At steady state, accumulation goes to 0. Formaldehyde here actually is a product in the first reaction and it is a reactant in the second reaction, which means within the reactor it is being generated and consumed. However, there is no input of formaldehyde for the system. So, input goes to 0. So, the output term we have would be equal to generation minus consumption. So, how do we calculate the generation term? So, the generation of formaldehyde would be equal to the consumption of methanol based on the stoichiometry. So, generation is equal to consumption of methanol, giving us a value of 90 moles. However, we have also been told that the actual yield of formaldehyde is 75% of the theoretical yield of formaldehyde based on methanol fed. So, this means we would have to assume the theoretical yield to be the amount of formaldehyde which would have been produced had the methanol been fully converted only to formaldehyde. So, this would result in 100 moles of formaldehyde being formed. We have been told that the actual yield is 75% of the theoretical yield, thereby what we observe as the output would be only 75 moles of formaldehyde. So, as I said, theoretical yield of formaldehyde would have been 100 moles. So, actual yield was 75% of that, giving you only 75 moles. So, the output NHCHO would be basically the actual yield, giving you 75 moles. From here we can calculate the consumption term as generation minus output, generation being 90 and output being 75, giving you 15 moles. So, this now tells you how much of formaldehyde is consumed by the second reaction. So, we can now write a carbon monoxide balance. The carbon monoxide balance would again start from input minus output plus generation minus consumption equals accumulation. Steady state accumulation goes to 0. We would not have any consumption because carbon monoxide is only being produced. There is no input for carbon monoxide, thereby your output is equal to generation of carbon monoxide. So, based on the stoichiometry, we know that generation of carbon monoxide will be equal to the consumption of formaldehyde in the reaction 2. So, generation here would be equal to consumption of formaldehyde, thereby the generation term is 15 moles. So, the output for carbon monoxide NCO would be equal to 15 moles. The next component for which we can write a balance equation would be water. So, let us write the water balance. Again, as usual, we start with the general balance equation, which is input minus output plus generation minus consumption equals accumulation. So, water is not consumed in the reactions, and at steady state there is no accumulation also, and there is no input of water, giving you output is equal to generation. However, water is generated by both the reactions, reactions 1 and reaction 2. So, for this reason we would have the output for water would be equal to generation of water in reaction 1 plus generation of water in reaction 2. So, generation of water in reaction 1 would be equal to the consumption of methanol in reaction 1. This is based on stoichiometry. So, this would be equal to consumption of methanol in reaction 1. So, we know that the consumption of methanol in reaction 1 is 90 moles. So, generation of water in reaction 1 will also be equal to 90 moles. Similarly, generation of water in reaction 2 will be equal to consumption of formaldehyde in reaction 2. We know that consumption of formaldehyde in reaction 2 is 15 moles. So, thereby giving the generation of water in reaction 2 to be 15 moles. So, the output is basically the summation of these two. So, NH2O is equal to 90 plus 15 giving us 105 moles. So, now we can write a balance equation for oxygen. Oxygen balance would be, again we will start off with the general balance as input minus output plus generation minus consumption equals accumulation. At steady state accumulation goes to 0. Oxygen is only consumed, it is not being produced. So, generation goes to 0. We have input oxygen in the form of air and we have output oxygen which is the unreacted air leaving the system. So, for this reason we would have output equals input minus consumption. We can calculate the amount of oxygen which is supplied to the system based on the information given to us in the problem. The problem statement tells us that air is supplied at twice the stoichiometric amount as what is required for complete conversion of methanol to the desired products which are fed to the reactor. So, now based on this information we can calculate the amount of oxygen fed as follows. Oxygen supplied, which is the input, is equal to 2 times stoichiometric requirement in reaction 1. So, from the reaction stoichiometry we know that every mole of methanol requires half a mole of oxygen for the reaction, which means when we are supplying it at the rate of 2 times. So, we have 2 times 0.5 which is the stoichiometric amount, twice the stoichiometric amount, times 100 moles which is the number of moles of methanol which is being fed to the system. We actually are supplying 100 moles of oxygen to the system. So, substituting the values back here we get output is equal to 100 moles minus consumption. Now, let us look at what the consumption would be. So, consumption of oxygen in reaction 1 would be half the generation of formaldehyde or half the consumption of methanol. So, this would be half times consumption of methanol, and consumption of oxygen in reaction 2 would be half the consumption of formaldehyde in the reaction. So, now having this information, the total consumption of oxygen would be 0.5 times 90 plus 0.5 times 15, giving us a total value of 52.5 moles. So, now the number of moles of oxygen leaving the system NO2 would be equal to input minus consumption. Input is 100 moles and consumption is 52.5 moles. So, NO2 is equal to 47.5 moles. So, the last component for which we need to write the balance equations would be nitrogen. Nitrogen is a non-reacting component in this system. So, you would have input equals output. So, we can write the nitrogen balance as input equals output, giving rise to calculations for input alone. So, based on the information we have for oxygen, we can calculate the amount of nitrogen. So, we know that 100 moles of oxygen is fed. So, this means this 100 moles constitutes 21% of air. So, the rest 79% is nitrogen. So, based on that information we can calculate input of nitrogen as 100 divided by 0.21 times 0.79, which gives us a value of 376.2 moles. So, N nitrogen which is leaving the system would be equal to the input, which is 376.2 moles. Now that we have the number of moles for each of the components in the system, we have to now calculate the mole fractions for this. Total number of moles in your product gas would be total equals N CH3OH plus N HCHO plus NCO plus N H2O plus N O2 plus N N2. So, adding all these values, we have 10 plus 75 plus 15 plus 105 plus 47.5 plus 376.2, giving you a total number of moles as 628.7 moles. Using the individual number of moles for each of the components and the total moles, we can calculate the mole fraction or mole percentage of each of the components in the product stream. So, the composition of the product stream using that would be 11.9% formaldehyde, 2.4% carbon monoxide, 1.6% methanol, 16.7% water, 7.6% oxygen and 59.8% nitrogen. So, this gives you the molar composition of the product gas which we have obtained through this process. With this, we come to the conclusion of the example problems where we use single unit processes with multiple reactions. In the subsequent lectures, we will look at multi-unit processes where reaction or a reactor is one of the units and we have other units. So, just like we solved for multi-unit processes without reactions, the critical aspect would be choosing the correct system. So, we will move on to that in the next lecture. Thank you.